What an honor and a privilege to be with you. Thank you so much for being with us. I think we have a very nice section today. Three presentations during the session organized by GSI. The first presenter will be Drew Loazzo, who's out of Propex in Chattanooga, Tennessee. He's going to talk to you in particular about introduction to HP-TRMs, but be very specific on the application. I'm subsequently going to do the second lecture and talk about lab testing, specification, and functional longevity of high performance TRMs. And then Joel Sprague out of TRI Environmental in the South Carolina lab. He's the technical director down there. He's going to talk to you about performance testing and then design. So it should be a good show for you. If you have questions, please do not hesitate to use the chat. We have Aaron taking care of things from the technical side, but Drew, take it away. Drew is the engineering service manager at Propex Geo Solutions. So hopefully we'll have a nice session. Thank you so much for being here.
All right, guys, thank you guys for your time. And thanks, George, for putting this together. As he mentioned, my name is Drew Loazzo. I'm the Engineering Services Manager here at Propex. And today I want to talk to you about the introduction to HP-TRMs, but more on the application side, how we use it. At Propex, my role is to help engineers, contractors, and other partners design for and use and install these types of materials well and appropriately. So the application side is really what we deal with on a day-to-day basis. So firstly, you want to look at this from understanding the challenge. Now, we're talking about erosion control applications specifically. We'll look at TRMs and HP-TRMs. For us to know what an HP-TRM is, we got to start with a TRM. We'll look at sort of how we design and how we look at the use of an HP-TRM, and we'll look at two case studies to sort of sum it up together. So obviously, the challenge we're looking at is erosion. Erosion can be caused from a lot of different things, but essentially our landscapes are changing. It could be from some natural cause or something that we do as humans to change areas that accelerates this process. Could be construction, could be areas where it's just not maintained over years. Some areas where we remove vegetation, include more impervious areas. There are a lot of things that can add to it, but we want to focus on erosion as that challenge that we're looking to remediate and to fix. You see the picture here. This is a project where just over years of time, rainfall on the slope has caused a lot of rilling to happen. This is not an uncommon situation. We see this all over the place in areas that need some protection against erosion. So just to be clear, this is not focusing on sediment control. This is erosion control. Erosion is that loss of soil, the particles, individual particles of soil caused by water or wind. For us specifically, we're talking about that more water-based erosion. Sediment control is sort of keeping it once it has been deposited and moved. So from our perspective with TRMs and HP-TRMs, you're trying to keep the soil on the slope before it has eroded and then deposited somewhere else. Some conventional solutions to erosion are hard armoring, rock riprap, concrete lining. There are lots of different solutions that are commonly used. Honestly, rock riprap is the number one thing that we see out there. And concrete and rock riprap both have their places and their uses. Our goal is to try to find a way to optimize that. There are a couple things that are challenging with using rock riprap and concrete. One is just their logistics. You have to have a lot of trucks, a lot of vehicles to move that, a lot of heavy equipment, which puts a lot of carbon footprint out there. The manufacturing of them is not always ideal either, with a very large carbon footprint as well. There are not a lot of environmental benefits to using solutions like these. So we're trying to find a way to optimize it, use rock and riprap and concrete where we have to, but looking at other solutions. And these solutions that we're looking to are turf reinforcement mats. We'll talk about what they are specifically, but an idea or concept, we're looking at reducing soil loss on a site prior to vegetation establishment, and then improving the vegetation as well as reinforcing the vegetation so it can perform to a higher degree with these different materials. So what is a TRM? Most of you guys probably know what these are, but a turf reinforcement mat and even a high performance turf reinforcement mat, these are synthetic materials that are designed to be permanent. And I'll say permanent as in it's going to be more permanent than something that's temporary. Depending on the product, the way it's used, the way it's designed, permanent can be 3 years, it could be 50 years. It just depends on the perspective of the product and how we use it. But again, we're looking at protecting the soil and seed before vegetation establishes. And then once vegetation has established, we're looking to reinforce it so that it can get to a higher level of performance. So you can see the graphic there with the vegetation growing through the material. That photo on the right-hand side is actually a project out in Kentucky that when you look at that, all you see is vegetation, but really what it is, that's a high-performance TRM. It also has anchors in it from a stability perspective, but that's a reinforced slope where that vegetation is being reinforced by the HP-TRM component in a situation where otherwise they'd have to use something like rock riprap or some other type of solution. So for the turf reinforcement map perspective, we got to start there in order to get to an HP-TRM. A TRM, like I said before, it's a synthetic material. There are a couple of different types of construction, but the most common are a stitch bonded material where you've got essentially 2 nets on top and then fiber in between. Sometimes you can have a 3rd net in between, and those are all stitched together. You can have a fused composite, but all of these are polymer based. The strengths can range anywhere from 100 pounds to 800 pounds, sometimes even more than that, pounds per foot of tensile strength. They do have some moderate UV stability to them, 80% at 1,000 hours for 40 through 55. That could be really a 3 to 10 year design life. They're really not designed to last forever, but we've had a lot of great projects with these TRMs where that have worked really well over the years. But we're looking at using these in lower flow applications. They can do great hydraulically, but their biggest weakness or area that we need improvement on is the strength, the ability to resist what we call non-hydraulic stresses, those areas that hydraulically we're fine, but then can we control the debris loading, the maintenance loading, the wildlife impact, things that are non-hydraulic in nature. And we'll talk about that more in a second. And so while these do great hydraulically, we're getting vegetation to establish. They were the first type of erosion control material that was developed years and years ago, but it's progressed to looking at a different material, which we've had, which is called a high performance turf reinforcement mat. A lot of times when we talk about performance, we automatically go to hydraulic conditions. That is a big component of it. We've done a lot of testing of these materials we'll get to in a moment, but really we're looking at performance as a whole. So that's durability, that's strength, that's hydraulics, all these areas. How can we have an elevated performance versus your traditional TRM? So an HP-TRM it's a synthetic material. It's very highly durable. The majority of them are woven 3D construction. There's some different photos of different materials out there. There are some other composites, but the majority of them that are used have that woven construction. One key differentiator is the strength, the durability. The minimum requirement for an HP-TRM is for the strength of 3,000 pounds per foot. So with these being woven materials and having multi-directional strength, you typically have a cross machine direction and a machine direction that has different strength properties, but both of them have to have a minimum strength of 3,000 pounds per foot. These typically have a much higher UV stabilization, usually a minimum of 90% at 3,000 hours and 90% at 6,000 hours. So what that is, and I think George might get into this a little bit more later on, 90% strength retained after 3,000 hours of accelerated exposure. Typically the method we use based on these colored materials having green and tan colors is ASTM D4355. That's a xenon arc weatherometer. There are other test methods out there, but with a colored component of it, it's really important to have that full spectrum. This strength and the durability we'll talk about in a moment, anywhere from a 50 to 75 year design life. So it's a much more durable, much longer lasting material than a typical TRM. From the application side, we're looking at higher flow channels, steeper slopes, more severe non-hydraulic stresses. An HP-TRM, these are the materials that the FHWA and the U.S. Army Corps uses when these higher stress applications. We're looking at heavy mowing and other areas. So a couple just quick shots of an application of an HP-TRM. Again, these are more highly critical, higher stress situations. The stresses could be hydraulic, they could be non-hydraulic, but generally it's a higher level of performance that's required here. Whether it's a TRM or an HP-TRM, the typical installation is pretty similar. So this is a photo that shows it, with great vegetation. But whether it's here out in the east or out west, the vegetation can vary. The installation can be similar, where you've got a trench really around the perimeter of the installation. These materials are installed with securing pins. The pins are temporary in nature. They're really designed to hold the material in place so that vegetation can grow through the material. And ideally, we're getting some form of vegetation. We call it a turf reinforcement mat. That sort of gets a bad name out west where turf doesn't exist. If it does, it's highly manicured and it's highly watered. But it's really about reinforcing vegetation, whether that's bunch grasses or small shrubs or just turf grasses like we have here shown. When we look at these products, we want to look at, and from my perspective as an engineer, trying to understand how we use them and how we use them well. So from a design criteria perspective, the first thing we look at is obviously hydraulic stresses. So this is your resistance to velocity and shear stresses. We want to make sure that we're using the right product. A lot of times when we look at a hydraulic application, we want to make sure that they're going to be used in a situation that's going to perform. If it's not going to meet the performance requirement, we don't want to use it. We'd rather use something else that's more appropriate. The big design question, though, for us is the non-hydraulic stresses. So are there any maintenance or installation equipment going to be on site? Is there any impact to wildlife that's anticipated? And then what's the requirement for design life and durability? So the idea is that these two pictures here, the project on the bottom left-hand side has a very high hydraulic stresses on it, but will those hydraulics necessarily tear the material? Maybe the mechanical connection that we have to the concrete structures that are adjacent to the bridge, but the water itself is going to cause erosion, and if it's connected somewhere, it might tear it, but the water itself is not going to directly tear the material. But on the right-hand side, that's a similar application where that front end loader is filling on top of the soil or the HP-TRM, but because it has enough strength, it can withstand the installation. So we want to find an application where if we need strength to withstand the installation or just the project itself, we have a durable enough material. The last thing we look at is geotechnical stability. So we're not going to touch this here, but if a slope gets too steep, erosion is not always your problem. You could have a superficial stability issue or a larger problem as well. So one great thing, and Joel will talk to this here later, is we've done a lot of testing. The first HP-TRM was developed in 1994, so over 20 years of experience. These are not new materials. We're always improving it and always understanding them more, but we had a lot of testing behind it hydraulically, whether it's unvegetated, vegetated, steady state, overtopping, unsteady state, lots of different variations. You want to always make sure that the product you're using has testing behind it so you can really understand that specific material's capacity. There's always a progression of things. Hydraulically, we've done great with different materials. Even TRMs can provide extremely high resistance to hydraulic stresses. We've done different tests without anchors, and we've done some here recently with anchors to see how that anchor improves things, and it really does make a difference. But these are not just your standard 6460 flume tests. We've seen with overtopping testing for the Army Corps that there's been a big improvement with these use of materials. So non-hydraulically, though, we're looking at maintenance, installation damage. Is there some stress that could potentially tear the material? If there is, that's where we're looking at using these higher strength materials. Wildlife impact. In some areas, there might be a tendency to have burrowing animals. An HP-TRM is a strong enough material that can deter that burrowing to somewhere else. We want to protect the wildlife, whether it's entanglement potential with other stitch bonded TRMs, but we also want to make sure that our infrastructure is protected appropriately. So we want to make sure that these materials can be used in these scenarios. Debris loading. Picture on the left-hand side, we'll see in a moment a little bit further. Debris after a large storm event, but the HP-TRM is still intact. Adjacently, we have a stitch bonded TRM. It's a great product, works well, but it could not resist the stress of that large coming down that channel during the storm event. So if it can't withstand that non-hydraulic stress and it tears, that big open area cannot withstand any hydraulics either now. Any mechanical loading, whether we're using it with anchors, whether we have a mechanical connection to concrete or riprap or some other hard structure, having that strength really helps manage that transition and transfer that load. And then lastly is design life. Design life is a huge component that we spent a lot of time on here over the past 10 years. And it's really based on 3 separate things. They're all together. The ultimate strength of the material, where it starts out, having a good quality manufactured material that you can have confidence in that starting tensile strength. Second is durability. That's resistance to UV resistance or UV stresses, but really it's all of sunlight. It's, can that antioxidant color package resist the environmental exposure and still maintain its strength? But that comes to fruition with looking at actual field performance. Put a product out there for 10 years and see how it works. That'll tell you a whole lot about a material if you can look at it in 10 years and see what's been going on. And then what strength do you need? If you put this out there and nothing ever touches it, I'm sure it'd be fine. But if you have any mowing activity, if you have any maintenance loading, you need debris loading, these things can potentially tear the material. And so you need enough strength to withstand that stress. And the idea is that you get something like this, and George has gone into a lot more detail of these things, but just simply starting out with a certain strength, expecting a certain degradation curve over time based on UV lab testing and field performance, and then seeing how much strength we need in that application to help us understand how long the material will last and function from the erosion control perspective. So there's a lot of information I threw at you, but I want to go through 2 case studies that shown how we've used an HP-TRM here historically. This first one was in Arizona back in 2010. This was installed in a channel application. So you see the channel here. It's a large area that really collects all the water and runoff from the solar panel areas out in Arizona. This was installed in 2010, so about 10 years, almost 11 years ago now. For cost comparison, this was 2010 estimated cost. The reason this was sought after and looked at, it was the big reduction in costs compared to rock riprap and articulated concrete blocks. Both rock and ACBs have their place, and we use them very often in combination with these systems. But if we can find a way to use, again, a more optimized design, we're going to have a better performance and reduced cost as well. So just showing the installation in November of 2010. Installation, you typically have the trench at the top of these channels on each side, and then overlaps, all of the materials pinned as well. So you can see some of the end overlaps and edge overlaps as they made that turn through the channel. Some more installation shots. Every so often we'll have a simulated check slot. I see those tight rows of pins, keeps the material tightened down and keeps the water flowing on top of it. Here's 9 years later. So this was seeded with natural native vegetation that could take hold. Obviously, this is not going to be the same vegetation you get out in the east. But this is 10 years later, or 9 years later. Great vegetation, not just grasses. You got some shrubs and small bushes as well. But you also have a lot of area that's exposed, and so we always want to get great vegetation, but we also know that vegetation is never constant. It's going to change from year to year. Different times of the year you might have more or less, and so we want a durable material that can withstand that exposure, even if that vegetation isn't perfect. And some more shots here, just with the solar panels in the background. And then we came back actually last year again for looking at 10 years of post installation. So you can see it's still there, performing well. Vegetation is growing and well. Good shot of just the solar panels and their application. But this is a use of an HP-TRM that was in the ground for 10 years and performing well. Again, able to give a huge cost reduction. So this is not a new technology. We've had it for years now, and we're really starting to see the benefit of the durability through the design life of these projects. One more I want to go through quickly is a project that really it's been through the years. It's been a process, I'll say that. So this is the progression earlier we've seen with the levees in New Orleans. So this was back in 2007. So for that, we had Hurricane Katrina come through. We all remember that. There's a lot of devastation, a lot of flooding. A lot of that was caused from overtopping. Overtopping of the levees came through, and the storm surge came up and overtopped them. But we really saw the really cause of things after everything dried up a little bit. these were the levees. The levees overtopped and started eroding from the backside at the toe, working its way back up. And so we saw a need. There was a need for protection. In 2008, this was a Penn levee in Lafitte, Louisiana. This was the backside protection. So this is not the wave impact. This is once it overtops, looking at protection there. So you see the protection here on the backside. Both the Penn and the camp levee was installed prior to, or once vegetation established. Then Hurricane Ike came through, came and overtopped the whole levee system. And in 2008, you see the same picture I showed before of that debris loading. Well, this is the system that it incorporates an HP-TRM. It's an HP-TRM with the earth anchor as well. So even though they had that debris loading, about a year later, vegetation had recovered. This is that resiliency that we've seen in the levees. Well, this led to the thought, okay, can we do more with that? You know, with that levee overtopping and it protecting and working well, what can we do to know more? This was a long effort from the Army Corps of Engineers, and they really wanted to vet these materials and really see how they performed in all aspects. So first they did, they did overtopping. This was a very complex hydraulic testing situation that was developed with the Army Corps and CSU and others to really simulate the same overtopping that happened in previous storm events. So this was a very intensive testing that they went through. They also went and did an installation and maintenance test. So they physically went out, installed the material with the same crew they maintain all the rest of their levees. They tried it and make sure that the strength of the material was enough to withstand the stresses of the tractors and the mowing equipment that they had to use on these levees from a normal application. They also did testing for wildlife resistance. For levees in New Orleans and other areas, burrowing of feral hogs is a big deal. They root in and they can cause a lot of damage. So making sure we have a material that is strong enough to make it difficult for them, and so they go somewhere else. While we love our animals, we have to protect the levees and infrastructure so that we protect our people. So making sure we have a material that is not going to hinder them in any way, but also encourage them to go elsewhere to root. So for perspective, this 80 miles of levee armoring came out. And so all the green you see there are levees to be armored with an HP-TRM and sod. Here's a typical section where the water is coming from left to right, where it's protecting on the backside for overtopping protection. Typical installation, we have the trench at the top, trench there at the toe, back past the toe, and the subgrade being prepared. You got the HP-TRM being placed in the trench first, installed with anchors and pins, and then throughout the face as well. Once the installation is done, making sure all the areas are marked and overlap is right, anchors and pins spaced accordingly. Anchors, we've made a lot of progress since then. You'll see some pictures in a moment with some different anchor installation techniques. A lot of improvement has had throughout the years. And then for this application, they're sodding directly on top of it. The use of sod, obviously it's one way to get vegetation to establish. There are a lot of other ways, but having enough strength to withstand the stress of that little sod layer puts on the material is important. We don't want to have material tearing while we're placing our sod for vegetation. So here's the installation sort of progression. Here are a couple of more photos of another application, another installation along this corridor. That's Lake Pontchartrain down the left. You see it start in New Orleans on the right-hand side. They've done a great job of the installation process here with such a large projects. They've got it down to a pretty exact science and pretty quick install. But you can see just the extent of the installation. Very large installation, multiple of these, where they're using HP-TRMs, by the hundreds of thousands of square yards. This is not a new system or new technology. It's been used very well, very successfully, and we're always learning. We're always looking at new applications, way to use it differently. But ultimately, we're looking at providing a higher performance from a durability perspective and strength, a hydraulic perspective, and then overall looking at a better factor of safety. We're looking at these critical applications, these infrastructure that is protecting our cities and our communities. Having that higher strength, higher durability really adds to that factor of safety. So with that, if you have any questions, I'm happy to go through those. It's a lot of information.
I have a question for you. The Corps of Engineers seems to have adopted your solution in big form. Do they have challenges to you that you haven't been able to address, or are there things out there that are still on the horizon?
You know, I'm not sure. And I know that the process has always been evolving. I know that, you know, this has not been a quick process. You know, the first installation was, you know, 15 years ago, more or less. So it's been a long endeavor. And I haven't been a part of it for the whole time, but for the more or less past 10 years, I've been involved in this side of things. And there have been challenges, you know, challenges in terms of the testing process and going through that and understanding, making sure that they get material they're looking for. I think some of the biggest improvements they've made here recently is on their requirements for durability. You know, when we're looking at these applications, this is a long-term solution for them. And so they're looking at something that has high durability. And so they've actually recently, they've increased some of their specifications on durability, their UV protection. You know, they require now not just third-party testing on UV, but also field performance, because they've come to understand, like we've talked many times, that you do a lot of UV testing, you can you know, show a lot in terms of on a product data sheet, but ultimately when you can show a product that's been installed in the field and performing over a certain amount of time, that's how we can connect our lab testing and make it relevant. Those two have to go hand in hand, and they've definitely seen that. We're always looking at different applications, you know, whether it's levees is one specific need, but we're also, you know, we've gone through channels with them, river banks, different applications there. But again, everything's always sort of progressing. And the HP-TRMs don't fit everywhere. There are times where ACBs are used on these levees. There are times where concrete is used. There are multiple systems used here for them, but that's just one aspect, one area that it fit well.
Fantastic. Thank you.
Yep.
Aaron, if you could swing us over, I'll start it up.
George, I sent you the request to share your screen. Perfect.
What an honor and a privilege to be with you. Thank you so much for the opportunity. I'm the second one in this lecture and talking about high performance TRMs. Aaron, it's not advancing.
Let's see, George, are you on, let's see, you have presentation mode shared. Do you have, is it frozen? Try hitting escape to get out of presentation mode for a second. Okay, let's try it again. Go ahead and share your screen one more time.
I'm going now.
Okay, can't
Do
see
you
your
see
screen.
me?
Can't see your screen right now. I can see you. Let's see. There we go.
Okay.
Must have just been a little hiccup.
Thank you so much for bearing with me. I'm George Kerner, director of the Geosynthetic Institute here right outside of Philadelphia. If you have questions, ask me up in the chat room. Questions are fantastic. Really enjoy them. If not, if you find things later, reach out to me via email, or I also answer the GMA tech line. So don't hesitate at all to contact me. We're frozen again, Aaron.
Is there a delay between when you click to move the slides and when it actually happens?
I have the audience view going across, and I have
Okay.
nothing advancing.
Are you clicking the mouse to advance or using the arrows on your keyboard?
The arrows. I'll just do it advanced with the arrows.
Okay.
Quest of all geosynthetic applications are really a credible analytic design, a simulated laboratory test, documented field behavior. Drew did an excellent session on that. But then we'd like to go forward and make a generic specification. And then in addition to that, once the specification has taken root, I think we need a guide for functional longevity. And this guide for functional longevity is going to lean on service life, and it's going to support sustainability discussions, which are based on benefit cost for these engineering decisions. An outline of the presentation. I'm going to talk to you about applications, products, then go into index testing. And then I'm going to talk to you about a generic specification for high performance TRMs, and specifically high performance TRMs. And then I'm going to talk to you about a guide that the Institute has compiled for functional longevity. At the end of the presentation, I'm going to talk to you about a little bit of commentary over the whole thing, recommendations and conclusions. But thanks for being with us. This is Joel Sprague in an old picture, but it talks to you about the two primary applications of channels and slopes. I love Propex's new symbol. It shows these applications in addition to where we're using them in infrastructure, in transportation systems, and geotechnical applications. So I think we're right on target here with a product that will be used and used quite well. The specification that I'm talking about is the Geosynthetic Institute's GRI GC14, and this is for turf reinforcement mats. It was adopted in 2015 and really had about 15 years of development. So I concur with Drew that these are not new materials. It's somewhat contentious. Please understand that this is a competitive industry. I realize full well that there are a lot of different manufacturers out there, but certainly to have a generic manufactured quality control specification, I think is needed in the industry to set a benchmark. Reasons for this, and tomorrow we're going to have a special session on just specifications, but I really think it provides clear instructions on intent and performance of the materials. It can be a reference for quality and a standard for which it's applied. It's a requirement for installation testing and could show a warranty for the material. This particular one does not show this. It can be used to support costing out of projects. If you know that your material meets this, it's sort of a level playing field for all people that are accepted. Its ability to minimize risk without a generic specification, you're in the Wild West, so to speak. And it improves efficiency for the manufacturer. He can stockpile, or he or she can stockpile the material and say that it meets that specification, and then have the material ready for a large project, several of which Drew showed you. This specification in particular for TRMs uses several categories, and these are categories for sheet flow and channel flow. It sets forth various physical, mechanical, and endurance properties. 8 specific test properties are required, and I'll go through them, and 3 categories are subdivided into severe, moderate, and least severe. The most severe case is the high performance TRM, and in truth, we had a discussion in ASTM D35 about a definition of an HP-TRM, and it's surrounded around this most severe category. Preliminary comments: the specification is silent as far as polymer type and formulation. There's a lot of technology that goes into these polymer formulations. Most of them that I see are olefins, but others are not. You have to leave it up to the manufacturer and give him some leeway in this regard as far as the formulation is concerned. It does not address natural fibers. I can tell you that all of this is geosynthetics, and they're polymeric materials, which we categorize. We're not addressing the natural materials. The tests are all ASTM standard, which are consensus standards, which I think is good. Joel Sprague, our last speaker, with his son, has spent quite a bit of time in ASTM D35 and D18 pioneering these standards, and my hat's off to him in that regard. Values are listed in American and SI units, but I can tell you the metric system is coming on full blast, and we're going to see a lot more of that in the future. As far as the sampling is concerned, it's based on an ASTM standard D4354, and while the tables are also based on MARV value, and I'll talk a little bit about that. MARV is minimum average roll value, and the TRM, it's for the property of the TRM. This is not the absolute minimum. It actually is a statistic 2 standard deviations away from the database mean. The procedure is shown in the next slide, but I think it shows you this. You have the average value, which is the mean value, and 2 standard deviations brings you into the 95% confidence level of this material. There is a guide to show you how you reach MARV and to addressing that on a site-specific scenario. The manufacturers, how many samples should you take? And it depends how big the job site is. You saw the job site for the Corps of Engineers on the back of the levee. That probably has over 1,000 rolls of materials, and this table from the ASTM standard would give you an indication of the number of rolls to take for QA. There's also a requirement as far as QC is concerned. This is a manufacturer's quality control specification. It's categorized underneath the label of GRI GC14. The 7 values that I'll talk to you about are listed here: thickness, stiffness, specific gravity, resiliency, tensile strength, the all-important one, number 5, light penetration, and UV. Thickness, again, an ASTM standard, different than the one from Geotextiles. It uses a very large pressure foot at 150 millimeters in diameter, 6 inches in diameter, a relatively light 0.2 kPa, and a dwell time of about 5 seconds. And then you're testing a minimum of 10 specimens. This is what it looks like. It's a dead weight micrometer with a large cantilever on it, but works quite well. As far as stiffness is concerned, again, another ASTM standard that worked its way through D35. It's D7748. The property which is called out is a flexural rigidity value, and basically you introduce the specimen into a bending moment. You do this in the machine direction and cross machine direction, and you also do it top and bottom, then generating an average value from this. Specimen looks like this. It's on a 100 millimeter 4-inch wide specimen, and you're looking at the bend to a known angle or inclination angle. The calculation of flexural rigidity is here. You're getting a bending moment, which is then the length of overhang divided by 2, and subsequently calculating a flexural rigidity. You need to know that value C, which is from the overhang divided by 2, and then multiply it by the mass per unit area of the turf reinforcement mat. Specific gravity is called out. I said most of these things are olefins. There are two test methods that are done. One is ASTM D792, which is a specific gravity test, or you can also use a more accurate test of D1505, which is a gradient column, both of which are giving you a density, and subsequently from that, you will find out a little bit about the formulation of the material and know a little bit about the control of the product. As far as resiliency is concerned, this is an index test as well, but giving a little bit of guide on how the material will respond out in the field. You typically have a presser foot, which you're cycling a load on, 3 cycles of a load over a given time increment. It's a dead load, and then you like to see how the material springs back. This will give you an idea of equipment going over the material, if the material maintains its 3-dimensional property, and it's key for the experiment. This is our apparatus at GSI. Use it in tandem with the thickness measuring device to give you a response. Tensile strength, and Drew called this out as a very important property. I concur with that. This performance is critical. It's a test method that's called out in D6818. You're going to need a continuous rated extension machine operating rather quickly at 300 millimeters per minute, 12 inches per minute. The specimen is about 4 inches by 6 inches. You have the jaws going totally across. You typically test it in the machine direction, but the user can call it out in both if he so wishes. This is it in a continuous rated extension machine, and you're pulling quickly on the material, and the grips cannot incipiate failure, and you'd like to see failure within the gauge length of the material. As far as light penetration, this goes hand in hand with the ability of the high performance TRM to vegetate, and it's called out in ASTM D6567. You have a light meter, a specimen. You're seeing the percentage that passes through into the light meter. There are lenses for it. It's a very prescriptive test and works quite well. This is the light box on the left-hand side. On the right-hand side is our setup here at GSI. An all-important property for durability is the UV resistance of the material. This test method has changed, has morphed in the specification. We originally started out with UV fluorescent, but with the properties that Drew alluded to in regards to color of the material, we changed the specification to xenon arc. It's called out in ASTM 4355. The exposure cycle is set up, and subsequently you're testing the material and the tensile properties to see its loss with respect to time. You'd like to see 90% of the original at 6,000 light hours for this class 1 or high performance material. UV fluorescent device looks like this. This is a rather old CI35. They have much newer devices out there. We typically go to either tensile properties of the individual yarns or the composite. We run it twofold for our particular testing. Commentary on this: there's a large variability of turf reinforcement mats out there. The 3 categories capture them, and the high performance one is the most severe category. GSI has evaluated a lot of products out there, and it's amazing that some products exceed these specifications considerably. We can't limit new and innovative products out there. Please don't think that a specification means that everything is over. This is certainly for commodity products, and there's still a lot of new innovation available to you out there. The specification looks like this. The specification on top is in English, and in bottom are the metric units. As I was mentioning, the most severe are class 1 or A characteristic. shows you that for high performance TRM. It's in lockstep with what Drew's comments were earlier as far as tensile strength being above 3,000 pounds per foot. I submit to you, though, that the entire column in most severe are requirements for high performance TRMs, and you need all of it to be within that class of material. So that's the specification. The next step, which I marched through in the outline in the beginning, is subsequently to determine the allowable tensile strength and then to get out of it some sort of functional longevity. This functional longevity is really a T allowable value to use in a design. The T ultimate value is from the test method. It could also be from a wide width tensile method, but then you're cutting it back with reduction factors. This guide is relatively new. GRI GS25 is relatively new. We could only get 4 parameters or reduction factors within the guide for consensus. Drew pointed out that there might be more, but these are documents and always in flux. As far as reduction factor for installation damage, creep, chemical degradation, which also includes UV, and then biodegradation involved with it. Examples of a small scale field project for installation damage. You can imagine the material can't have holes in it once it's installed. It has to be robust enough to handle this. There's an ASTM as well as a British standard for this. Both are in sync for that. The next property, polymeric materials, especially if they have sustained loads on them, will creep. There are several creep methods available to you with the inside of D35 as well as ISO. The method or the creep of the material will be heavily dependent on 2 parameters. 1, the polymer type, and number 2, the loading. You see the 3 different types of creep here. Conventional creep on the left, time temperature superposition in the center, and then subsequently on the bottom, stepped isothermal method. All 3 of these have application into this area and are addressed with inside the guide for correlation. UV is in several different forms, as we mentioned. The UV that's characterized here is for xenon arc weatherometer. Please realize there has been quite a bit of work done with UV fluorescent and outdoor exposure. So we're getting a lot of data and feedback from all these different scenarios for high performance TRMs. It's amazing how some of these materials perform extremely well. ASTM standard as far as chemical resistance is concerned, please realize you have a plethora of information from both a laboratory immersion and a field immersion associated with this. There are 2 procedures for that, and then subsequently a test protocol for your materials, all covered under D5819 within ASTM D35. As far as the durability of the material, we can also look at viscosity and CEG, and that works along with the different materials. As far as biologic is concerned, we're very concerned twofold, one from animals, but the second from microbes. So you'll see both of this in the biologic section of the guide. So you'll need to know what is the extreme cases. Moss will eat the natural materials. We had birds with inside the polypropylene. You have fungi and algae. Very few things eat the polymeric materials as far as microbes, but we do have a lot of vegetation growing into the annulus. We like that with some geosynthetics, we don't with others. As you go up in the food chain of into mammals, you see that some rodents, particularly muskrats, will burrow through HP-TRMs. This particular slide where you see the pond liner had an elk down into the reservoir. The water looked attractive to him. The elk couldn't get out, so he destroyed the geosynthetic in the getting out. This occurs also. A hoof of an animal is quite an impact to withstand out in the field, so we need more information on that. All of this tailors into another topic that Drew brought up in his presentation of exposed lifetime studies. We need some real case histories for these high performance TRMs. We had a very friendly owner of a large municipal solid waste facility just north of here who allowed us to do studies, which started back, I can't believe, 8 years ago already. We have 8 samples of HP-TRMs on the particular sites. Where they are is on the surface of a mechanically stabilized earth berm out in the field, and seeing the response with respect to time. Here you see the 2 different sites, an aerial view on top, and then up close. We subsequently bring these back into the laboratory and test them over time. Drew did not let on that these materials over 8 years haven't moved a bit. You know, this is going to be an extremely long-term study, and you need to be patient if you're in this business and you've formulated the materials quite well. We have this for erosion control and various products for design for slopes and channels. These materials are working very well, and certainly our focus is on HP-TRMs, but certainly it can be broadened to a bunch of different materials, and we'll see how the defining of these materials goes inside of ASTM. As far as recommendations are concerned, predictable performance is the quest. I think by these 3 items which we've talked about here, a generic specification, a guide for functional longevity, and then subsequently field case histories will really prove the point for turf reinforcement mats. I believe you see index tests, which are in very good shape for manufacturing quality control. The laboratory performance tests are available for you. Joel will talk to you about field performance in the next slide, these large scale tests. Please realize that there is seasonal timing, and maintenance is critical for all these sites. Drew showed a very nice slide of vegetation. It's often not predictable, but these HP-TRMs are performing vegetated and non-vegetated and really can work over time. There are a lot of commercial information out there on the installation, which is available. I love sending people to YouTube because I think it's very informative of what's out there and what can be used. Conferences like this obviously are extremely valuable. So in conclusion, HP-TRMs are indeed bona fide engineered materials. As such, they must be tested and designed accordingly to give a factor of safety. Regulations and permits are based on this methodology. I see that used in both EPAs and DOTs throughout the United States, and for that matter, the world. Obviously, big users of this are the Corps of Engineers and Bureau of Reclamations. Also, these agencies really like these materials and sort of the green or soft nature of that in contrast to riprap and concrete. But Drew played it very nice that you might be using a bunch of these different solutions in tandem. This is a partnership, obviously, which is sometimes difficult between a lot of different parties or stakeholders, the designer, the specifier, the installer, and the inspector. Good communication is important between all these various groups and certainly should be warranted. That said, let's make it work. These are good possibilities. Get involved with these groups. I've talked to you about ASTM at length, but both ASTM and ISO are volunteer organizations. Certainly work with them and work alongside all of us. I would like to acknowledge and sincerely thank the consortium of members at the Geosynthetic Institute. They support me and let me do things like this. Thank you so much. Let's discuss, and I invite any questions at this time. I don't see anything in the chat right now, but I certainly will take any questions that you have.
Well, George, this is Joel. There have been a couple questions that have come in, and we may want to get back with Drew at the end of the session. But one you might want to tackle is contractors complain that they cannot get good vegetation to establish with TRMs that are all synthetic or have heavy coconut fibers. A lot of times vegetation cannot get through the product to grow. Do you have recommendations on what a contractor can do to get good vegetation establishment?
The big thing is site preparation. You have to make sure the material under is receiving it and is not rolled flat. It's not good for a vibratory steel reel roller to go up and down this thing. That's the first item. Then proper installation for the manufacturer, and then typically an infill. This infill can be as much as what you saw on the previous slide of Drew's. But what you need to do is have a proper infill and then subsequently vegetate it with a mulch or a hydroseed, which you've seen. I have to say that this is extremely regional. As a geotechnical engineer, I should stay in the Northeast where I'm familiar with the soil properties. You really need a local to help you out in this regard. And then in regards to the HP-TRM, make sure it has its three-dimensional structure and make sure it has it's big enough light penetration. If it's not giving you that, go back to the manufacturer and make sure that it conforms to the specification. But that's the rung of areas that I'd look at, Joel. Thank you.
Yeah, I would also add, I completely agree that it's regional. Every area is a little bit different. Every project's a little bit different. Just to reiterate what George's saying, your preparation is critical. We deal with lots of projects in different areas, and anytime that we have an issue with vegetation establishment, I can almost guarantee you that if you start going and asking through the questions of things, there's something that's missed. Whether it's did you prepare your subgrade and make sure that it's not just void of any organic content or the wrong pH. You have to have good organics. You have to have the right pH for vegetation to germinate and establish. Asking questions like, what's your watering program? Vegetation has to have water to start vegetation, to start growing. Once it gets going, then obviously, hopefully nature can take its course and keep going, but you've got to have that to get that germination to establish. And then a lot of times there are different techniques. You can use hydroseed or hydromulching of some sort. You can use topsoil and other materials combined with it. But every project's a little bit different. There are some tried and true techniques that we've had success with in different areas. But if you go out to the east versus out west, your process is going to be different. So definitely getting a little local, regional here, just to reiterate George, that knows the area, knows vegetation. You want to make sure you got a local. That's going to make a big difference.
We have seen an exception for biomass and biosolids to be used in conjunction with this. You have to get buy-in from your local EPA. The runoff from this will probably contain metals, but if that's contained at a solid waste facility or into a diversion swale where you can control it, it sometimes gives you a very attractive vegetation very quick with very little water, and certainly is one hand washing the other in municipalities, which I might say are sort of brownfield sites, but it's an interesting area to look at. There'll need to be a ton of communication with the people with the shareholders that are involved. But I was just involved with a recent project with that, which was a very tight window after Thanksgiving growing season in the Northeast, which made the project work.
George, there are several more questions that probably go to Drew, but there's one that I think you are especially poised to comment back on. It's a comment that says HP-TRMs don't have to be woven. There are other forms that meet the requirements. For example, open fuse materials, thermally fused to a geogrid, or wire rockfall netting. Do you want to comment on that relative to your specification?
I agree on this, and you know the specification needs an update. It's a living document. Yes, the specification favors the woven products. It probably needs a task group on it to open this thing up. You take what you can get though with these specifications, but I hear you loud and clear, and I imagine future revisions of this will this HP-TRM could morph into a woven product, could be and then several other products, much in the same regard that geomembranes is broken down into HDPE, linear low density, chlorosulfonated polyethylene, and so forth. You really aren't comparing apples to apples when you cross over these different materials, and most function quite well in that regard. So there's work to be done, is what I'm trying to say. Thank you, Joel.
Sure. Maybe we move on to the last presentation, then see if we have time at the end for some more questions.
Great.
Okay.
My name is Joel Sprague, and I'm Technical Director over Large-Scale Testing at TRI's South Carolina Laboratories. We specialize in performance testing of erosion control products and sediment retention devices, along with a wide variety of stormwater control measures. Today, I'd like to discuss performance testing and associated channel lining design associated with high-performance turf reinforcement mats, also known as HP-TRMs. An HP-TRM is a type of rolled erosion control product, or RECP, that is made to be especially long-lasting and to have relatively high strength. While HP-TRMs have numerous important applications, the most common is to prevent channel erosion. This table shows why TRMs, and especially HP-TRMs, have become so widely used for erosion-resistant channel linings. Reinforced turf can provide erosion protection under hydraulic shear stresses as high as 11 pounds per square foot. This far surpasses vegetated channel linings, whether they are produced by conventional seeding and mulching techniques or enhanced with natural fiber rolled erosion control products. In fact, reinforced turf provides much more protection than even typical rock riprap. Even though the most versatile and economical channel lining is vegetation, it has limited ability to resist concentrated flows from stormwater runoff. As the intensity of storm events grows, drainage channels are subject to ever greater flow-induced shear stresses, often exceeding their erosion resistance capabilities. And when vegetation by itself is insufficient to handle a large storm event, tremendous damage can result. This is where the enhancing properties of TRMs that improve and extend the performance of vegetation are imperative. TRMs can provide both root and stem reinforcement and tie the vegetation together in a continuous, stable, vegetated mat. Still, not all TRMs are alike. and it is important to design for the project-specific performance required. The appropriate design approach is to select the channel lining that has a proven permissible shear stress level greater than the channel's flow-induced shear stress. This can also be referred to as stable channel design, or simply permissible shear design. The designer determines the maximum flow depth expected in the channel based on the known channel flow, cross-sectional area, longitudinal slope, and approximate roughness. Using the maximum flow depth, the actual flow-induced shear stress is then determined. This permissible shear stress of the candidate channel lining must be greater than the actual shear stress to assure channel stability. Over the years, various channel lining materials have been evaluated by independent researchers and approximate performance capabilities determined. General permissible shear stress ranges for generic categories of temporary degradable rolled erosion control products have been shown to be able to resist up to, about 3 pounds per square foot of hydraulic shear. Permissible shear stress ranges for generic permanent, non-degradable rolled erosion control products, also known as TRMs, have been shown to be dependent on the level or phase of vegetation achieved, and able to resist up to about 10 pounds per square foot of hydraulic shear when fully vegetated. Yet, accurate product-specific performance capabilities can best be determined using standardized, large-scale testing. This also assures meaningful product-to-product comparisons and facilitates selection of the most cost-effective product for a specific project. For standardized testing of large-scale channels, ASTM D6460 is used. This standard is titled The Test Method for Determination of Rolled Erosion Control Product Performance in Protecting Earthen Channels from Stormwater-Induced Erosion. The test method uses rectangular flumes, commonly having longitudinal slopes of 10% when testing unvegetated conditions and up to 20% when testing vegetated conditions. The minimum flume width is 2 feet. Each unvegetated test setup must be run 3 times, but vegetated setups need only be run once. Each test includes 4 increasing shear or flow levels, with each flow lasting 30 minutes for unvegetated test setups and 1 hour for vegetated test setups. The threshold for establishing the permissible shear stress is that shear stress that causes 1/2 inch average cumulative soil loss over the test section. It should be noted that D6460 allows various soils to be used in the testing, but most often a loam soil is used. Here's a typical view of 10% channels being used to test a typical RECP in the unvegetated condition. The RECP is anchored according to the manufacturer's recommendations, commonly using U-shaped pins in a diamond pattern. Flow depth and flow velocity measurements are made during each flow event. And soil loss measurements, via measuring the distance to the soil surface, are made after each flow event. According to D6460, 4 flow events are used to complete each test series. Triplicate channels are tested, and when very high flow rates are required, circulated flows may be necessary. The tractive shear forces caused by the flowing water can have significant effect on the protective fibers in the RECP. When the anchorage or the RECP construction is insufficient, the soil surface may become exposed directly to the flows, accelerating the erosion process. All types of RECPs may be tested using ASTM D6460. Vegetated TRMs may also be tested. Typically, vegetated TRMs must be exposed to flows in steeper slope flumes, up to 20%, in order to generate sufficiently high hydraulic shear stresses to cause significant soil loss. The results of the D6460 test series, that is, 4 sequential increasing flow events, are then plotted on a cumulative soil loss versus shear stress graph. By adding a best fit regression curve to the data points, the half-inch intercept can be found, which determines the product's permissible shear stress. A large body of D6460 data is available for a range of RECPs, including TRMs and HP-TRMs. The data can be found at ntpep.org. Here is a key to many of the types of RECPs tested. Each blue bar on this graph represents the average of all the D6460 tests run on a single type of RECP in the NTPEP program. The higher performing TRMs are shown to the right side. Clearly, triple net products and three-dimensional woven products provide significantly higher permissible shear stresses than do single and double net products. Now consider the dramatic increase in permissible shear stress when vegetation has had a chance to germinate and grow within the products. The gray bar represents 6 weeks of vegetative growth, while the green bar represents a full year of growth. Notice that 1-year vegetated TRMs consistently have over 10 pounds per square foot of permissible shear stress. Still, large-scale performance tests are relatively expensive. What is a product manufacturer to do if they want to determine the effects of performance on changing fiber or yarn supplier, changing the frequency of stitching, or increasing or decreasing the mass per unit area of their product? It would be cost prohibitive to run large-scale tests on possible product modifications. Thankfully, there are standardized bench scale index tests available to look at these effects. These tests can be used to look at slope erosion, channel erosion, germination, and biodegradation. The standardized bench scale index tests primarily applicable to TRMs are the channel erosion and germination tests. The bench scale channel erosion test is ASTM D7207, and the bench scale germination test is ASTM D7322. Let's look a little closer at each of these. ASTM D7207 subjects both bare and RECP protected pots of soil to hydraulic shear stresses caused by the rotation of water inside a tank by an impeller blade. Shear stresses below, near, and above the stress that causes the equivalent of 1/2 inch of soil loss are used. 3 pots are exposed at each shear level and, like with large-scale testing, the soil loss versus shear stress is plotted and the 1/2 inch intercept is determined with a best fit regression curve. Soil loss is determined by weighing the soil pots before and after a hydraulic event. An elevated platform holds the pots. The candidate RECP is then deployed over the pots and held in place using a plate with cutouts for the areas corresponding to the pot locations. The tank is then filled to a prescribed depth of water, and the impeller blade causes the water to rotate. The shear tank can hold 6 pots, and new pots are used for each shear level. Here you see the typical effects of shearing on the surface of an REC-protected soil pot, before shearing in the upper photo and after shearing in the lower photo. The relationship between impeller revolutions, RPMs, and the associated shear stress on the tested product is directly related to the roughness of the tested material. To determine this relationship for each type of material, an extensive calibration phase is required. The horizontal force caused by the rotating water shearing across the RECP mounted to the top of the pot at a given RPM is measured using a load cell mounted to the bottom of the platform. This is repeated at low, medium, and high RPMs for each type of RECP to determine the relationship. As noted earlier, soil loss at shear levels well below, near, and well above the threshold half-inch soil loss equivalent, which is 450 grams of soil in the pot, are plotted, and a best fit regression curve is used to determine the half-inch intercept and thus the permissible shear stress. So, the natural question is, do bench scale results correlate well with large scale results? This plot of average results for several types of RECPs shows that the correlation is pretty good. For most RECP types, the results are very similar. Still, it should be noted that large-scale testing is done with a loam soil, and there are many fewer tests for each type, while bench-scale testing is done with a silty sand soil, and the products are retested every 3 years. Also, samples taken for large-scale testing were taken from different rolls produced at different times than samples taken for bench-scale testing. So, a very limited study was done to compare the two tests using RECP samples cut from the same rolls for both tests. This approach better provided for comparing test results using the same RECP. 3 RECP types were compared. This plot of the study results seems to corroborate the more general findings that the large-scale testing and the bench-scale testing produce very, very similar results for permissible shear, and thus bench-scale testing can be a reliable tool for examining the effects of product changes on performance. The other standardized bench-scale test that is especially important to TRMs is ASTM D7322. The T in TRM is, of course, turf, suggesting that the performance of these products presumes that a robust stand of vegetation will be achieved. Rather than presuming, D7322 provides an objective measure of a TRM's ability or inability to nurture a robust stand of vegetation. 8-inch pots of soil are prepared with surface seeding, with and without the candidate RECP covering the surface, and exposed to a challenging temperature and humidity environment for 21 days. Data is gathered every 7 days, including the number of seeds germinated and the height of the plants. And at 21 days, the plants are harvested to determine the total biomass produced. The REC protected pots are compared to the unprotected control pots to determine the percent improvement associated with the tested RECP. It is important to note that performance of an RECP is heavily influenced by anchorage. Flowing water induces attractive shear that tries to peel the product off the soil. Thus, it must be adequately anchored. Early installations used wooden stakes, but the search for economy soon led to the use of light-gauge U-shaped staples. More recently, specially designed anchors have been used more frequently, especially when high flows are expected. And as shown in this graph, the pull-out performance of various anchor types can vary widely. Staples, pins with washers, and J-hook rebar typically provide the least pull-out resistance, while wood stakes and spiral screw anchors provide greatly enhanced pull-out resistance. Along with the proper selection and frequency of anchors, the use of anchor trenches at strategic locations can assure expected TRM performance is obtained. The upper and lower ends of installations on steep slopes and channels are important locations for an anchor trench so that the mat doesn't get undermined and pulled downstream or undercut and subject to scour. Anchor trenches at intermittent locations forces flow to stay on top of the matting and prevents continuous rilling. Most channel installations require a large number of anchors to assure that the matting will stay intact and in place. But providing this proper anchorage can be time-consuming. Thus, careful inspection of the finished installation is essential, especially in deeper channels. And other high-energy applications, such as culvert outlets. Recently, high-capacity anchors have been combined with high-performance turf reinforcement mats to optimize erosion resistance in special conditions, such as steep slopes subject to overtopping flows. These high-capacity anchors are referred to as percussion-driven mechanical anchors, PDMA. Here's how the PDMA anchor is installed to generate very, very high anchorage. The anchor is driven into the ground by a rod inserted into the back of the anchor. After the rod is removed, the tendon is tensioned to flip the anchor 90 degrees. The tendon is further tensioned to stress and activate the soil. And the top termination is locked to the tendon to maintain tension within the system. Here's a graphic showing the use of PDMAs along with a HP-TRM in a demanding levee overtopping application to resist backside toe of slope scour. High-energy applications like culvert outlets not only require special anchorage, but they also require a special assessment of the TRM's ability to resist the unique scour forces encountered. Unique large-scale tests have been developed to make these evaluations. Here's an example of large-scale testing of an HP-TRM to protect against culvert outlet scour. Installation of the system components is done as directed by the manufacturer, and then the system exposed to incrementally increasing flows. As with channel testing, flow velocity is measured during the flow event, and then soil loss is measured at the end of each flow event by measuring the distance to the soil surface from a baseline established prior to initiating flow. Performance results are presented as the cumulative soil loss resulting from each flow event. Other high-energy applications include the use of HP-TRMs for protection against spillway flows and levee overtopping. Once again, not only is special anchorage required, but a special assessment of the TRM's ability to resist the unique scour forces encountered must be done. Unique large-scale tests have been developed to make these evaluations. ASTM D7277 and D7276 provide testing and calculation methodologies to look at spillway conditions, and the U.S. Army Corps of Engineers wave overtopping apparatus can evaluate product-specific performance in preventing backside toe of slope scour. HP-TRMs are being used to protect against some of the harshest hydraulic conditions and, when combined with robust vegetation, are proving to be effective at controlling erosion and preserving soil stability. Thank you for your interest in this important geosynthetic technology.
Okay, folks, if Drew, George, and Joel can come back on camera. We can address some questions.
Sounds good. We had a couple questions. If you're okay, if we go through some of the ones that we were found out a little bit later, early in the presentation. I think we answered a couple of them. There was one question specific to sort of an environmental question. It says, can any of the speakers talk more to the issue of HP-TRM use with respect to wildlife? There's an increased awareness that synthetic materials and geosynthetics used in erosion control materials are harmful to and threaten endangered species, such as snakes, turtles, etc. Regulators are pushing for the fully degradable materials and are prohibiting biodegradable plastics. I'll start with this, and then obviously George and Joel, please jump in. It's a really big point because we want to do well with our materials and provide better performance, have good cost reductions, and have a whole project as a whole that works well. But we also can't do that at the expense of the environment. There's got to be a balance there. And so from a wildlife perspective, there's been a decent amount of research done on specific to endangering species of entrapment potential with stitch bonded materials, open weave materials, things that have essentially openings large enough to potentially have entrapment of smaller animals, snakes, reptiles, lizards, different things, different animals. And a lot of it has found that if you can get to a tighter construction where you one, don't have the ability for those small animals to get entrapped, but also have more of a flexible connection. So a stitch bonded TRM has small, more or less half-inch openings, quarter-inch openings, but they're rigid, they're fixed. Having a material like one reason they go to something like a jute is because it has a flexible connection point. So if you can go to a material, a lot of the woven materials have some flexibility to them, have a tighter construction, and don't have the tendency to entrap animals. We've had a significant amount of projects that have been approved using the woven HP-TRMs that don't have that tendency to entrap wildlife in California and Australia and other places where wildlife entrapment has been a very big concern. It's a real question. It comes up pretty often.
I might just add that as the contract lab for NTPEP, we kind of get to see some trends developing earlier than the general public, and there's definitely an uptick in products being submitted to the National Transportation Product Evaluation Program using organic netting materials in the last year to 2 years. So the questioner is right on as it relates to the more degradable materials.
And another balance I mentioned, sorry, George, real quick, the balance of environmental versus protection, and we want to strike that balance somewhere, is that if you're using a biodegradable material, we have to understand that has a life to it. It's going to degrade at some point, and if you're relying on that to reinforce vegetation to improve that hydraulic performance, it's only going to last so long. And so you're ultimately relying on vegetation at that point. Some applications that's okay, but some applications you need higher performance, and so striking the balance of performance versus environmental impact, it's somewhere in between.
I should push you further as far as the geosynthetic materials. They can't harm the environment. There can't be a compound being emitted from them. Some plasticizers, things like that. The material has to be sound. It has to be manufactured in a plant that does not harm the environment in that manner either. So it sort of morphs the question further, but make sure that the plant also is conforming to regulations in that regard too. But great question. Mark Tyson asked in regards to vegetation is so important. Why isn't it included in the specification? It's a good point. It is critical for the material, and certainly these are living documents, which the next revision can certainly see that. Love to work along with the entire group.
I would also add it's the vegetation part is challenging, as we talked before, that very often it's regional. So vegetation in the Northeast versus the Southeast versus the West or the Midwest, those requirements will all be different. They're also project specific too. It could be an application where you could get the performance you need out of 20% vegetation on one project, and then you need 80% on the next project to meet that same design threshold. So there's a lot of variability in there, which makes it challenging.
Joel, you have to give it up. It's pretty challenging in the laboratory to get it consistent as well.
Yeah, we've got it easier than in the field, though.
TRI, yeah, very true.
Drew, you might just take the last one. There seems to be some real interest in the sod use over top of the HP-TRM. Can you kind of give a little more on that?
Yeah, sod's not used everywhere. It depends on where you're at. Some places it's more readily available, some places it's cheaper, sometimes it's more expensive. But sod has, for some large projects, really simplified the vegetation part of it. The majority of the time, sod is placed directly on top of the TRM or HP-TRM. Sometimes there will be a requirement for soil fill. That's really only when the sod is not, there's not enough soil within the sod itself. Most of the time, there's a specification for the sod to have about an inch or so of soil within that sod mat. Sometimes they'll skimp on it and you need a little bit, they'll have a little bit thinner section of sod. And so to make sure that sod has enough soil to keep going and growing and being healthy, you need to put a little bit of extra soil. But if you can control that sod specification, it's usually installed directly on the mat. It doesn't always have to be pinned in place or stapled in place. It could be, depending on the hydraulic nature of the application, if it's near an outlet or somewhere where it's steeper, you might need some additional sod staples just to hold that in place while it vegetates and roots into the material. But it does really well to, really within a couple of weeks, rooting into the HP-TRM and growing through that into the soil below.
There was a question by somebody, is there a handout for this? Aaron told us, who's managed this session very well from IFAI standpoint, that all of these are recorded and will be available to the conference attendees. So you'll have better than that.
If I can also jump in there, the Geosynthetics event website will be updated at some point in the weeks after the show to include links to both the recordings and any PDF slides or other handouts that we have. So we'll make sure that we're in contact with everybody when that happens.
Okay, we're at the appointed hour. Thank you so much for the session participants. In particular, the presenters are just fantastic. The two bookends were great. I don't know, I was sort of slacking it in the middle, but these two gentlemen that I worked with have a tremendous amount of experience, and it was an honor to work with them. Thank you for the event. It's not in person. I wish we can get in person soon, but stay safe and use these materials with confidence. Thank you.
Thank you all.
Thanks.